Understand group actions a little bit better. So let G be a finite group, and it'll act on X, a finite set. Then the size of the set is the sum of the sizes of the distinct orbits. So these are the distinct orbits. An orbit, remember, is the set of everything you can get of the form Gx, where G is in your group. So these are the distinct orbits. Some of the orbits maybe have size 1. Maybe there's only one element in the orbit of a given x. Maybe these are bigger than 1. But what I'm going to do is I'm going to group all the orbits of size 1 into a single set. Let me call it x sub g. And then I will add the rest of the orbits together. So these are orbits of size at least 2. And I'm going to define xg to be the union of all the orbits of size 1. And what that means is that it's the set of all elements in X such that Gx is equal to X for all elements in your group. It's the union of all orbits of size 1, because to be an orbit of size 1, then Gx equals X for all elements in your group. All right, let's see an example of what I mean by this. So here's an example. Let's let X be the set B1, V2, V3, S1, S2, S3, F1, and F2, where these are the vertices, sides, and faces of an equilateral triangle. So this is like V1, V2, V3. This is side 1, side 2, side 3. Inside the triangle will be face 1, and outside the triangle face 2. So then the group Z3 acts on X by rotation. I could take the triangle, rotate it, change vertex 1 into vertex 2 into vertex 3, and so on. So what are the orbits? The orbits are the orbit of face 1. Now, if I rotate the triangle, face 1 is always going to stay face 1. So the orbit of face 1 is just the set F1. The orbit of face 2 is just F2. The orbit of vertex 1 will be the 3 vertices. In any order, it's a set. Because I could take V1 and with a rotation change V1 into V2. I could change V1 into V3. So these 3 elements are in the orbit of V1. And the last orbit is the orbit of the sides. So I have 4 distinct orbits. 2 of them are size 1. So therefore, using this notation up here, the set X sub Z3 is the set F1, F2. It's the elements in X that are fixed under any element of Z3. Any element of Z3. So it's like the fixed point set, but it's for all elements in your group. So here's a lemma. Let G act on X and say that the size of your group is a prime power. The conclusion is that the size of X and the size of XG are the same working mod P. So this notation means that the remainder after the size of X is divided by P is the same as if the remainder of XG is divided by P. So let's see if that's the case in this example. So here the prime is 3. So 3 is P and K is 1 in this example. So I have 3 divides Z3. That means if I divide X by 3, it should be the same remainder as if I divide the size of this set by 3. We could see it's true because I have 1, 2, 3, 4, 5, 6, 7, 8 elements in X. So that's 2 mod 3. And the elements in this set number 2 mod 3. So here's the proof of the lemma. So here's a proof of the lemma. I'm going to use this equation up here. I'm going to use this equation right up here. So the size of X is given by this size of this set plus all the orbits of size 2 or bigger. This should remind you a little bit of the class equation. We use similar logic to get the class equation. But so all these orbits are size 2 or bigger. Now, because of the orbit stabilizer theorem, this is the same as the size of this set. And for each of these, I'm going to write it as the size of the group divided by the size of the stabilizer subgroup. What we did here is we used the size of an orbit is the same as the number of left cosets of the stabilizer subgroup. And that's the size of the group divided by the size of the stabilizer subgroup. But the key realization is that the size of the group is a prime power. The stabilizer subgroup is not the whole group. So that means each one of these are all divisible by P. These are all multiples of P. Multiples of P. So that means we have some multiple of P. And that's the proof. That's the proof. So, conclusion, the size of X and the size of this set are the same mod P.